Dear students, so in the last video we have seen a sample problem of how to use strain energy method to solve or analyze an indeterminate structure. So we are going to see another problem. So here also we are considering a propped cantilever, okay, and here we are making a small change, that is a propped cantilever with a overhang, okay. This type of beams are called as beams with overhang, okay. So there's a beam with overhang, and let this be 5 meter, and let this be say 2 meter, and we will also have different cross sections or different material properties. Say for example, this portion is having 2 EI and this portion is having the property EI, fine. And let the load be say a UDL over the entire span, similar to the case of the self weight. So you can also consider this beam is having some self weight, and because of the self weight the beam is having some deflections, slopes, and also it will exert reaction. So we are going to consider that case. So let this value be say 2 kilonewton per meter. So this is the problem that we are going to analyze, and we are going to use the strain energy method to solve this. So let's see how to do it. So we have seen the procedure and all we know. In the last problem we discussed that. So the basic equation what we will be using is the theorem of least work, that is dou U by dou R is equal to integral m dou M by dou R dx by EI. Fine. This can be rewritten in a format like this: m dot dx by EI. This is also another representation for the same equation that we have seen, okay, where m dot represents the first differential. You might be familiar with this concept. So when we are talking about displacement, velocity, and acceleration, we use the same concept. So we call it as x dot, and acceleration we normally call it as x double dot. That is, differential of displacement will give you velocity. Second differential of displacement will give us acceleration. Okay, so this is one type of notation. This x dot means the first differential, x double dot means second differential. Similarly, this is the first differential, so even if we call m dot, that is fine. That is for convenience we are writing it like this. This equation can be rewritten in this format. You should not get it confused as small m. Okay, if you are using small m here, it becomes the unit load method. So first thing, we are going to convert this into beam of forces. So what we have is the beam. A fixed strength is going to have 3 reactions. This is a roller that will be having 1 reaction, okay, and we have the load. Now we want to think, or we want to identify the redundant. So how many reactions are here? Just if you are numbering the reactions, or I'm naming it, let this be A, B, and this point be C. So this is RA, HA, and MA. This will be RB. Now we need to identify the redundant. So we will just see the beam given in the problem. So if we are removing this support, okay, now it's a cantilever, which is a determinate structure. There are basically 2 determinate structures: cantilever and simply supported beam. All other support conditions are indeterminate. Fine. So this is now on removing this, it becomes a cantilever which is determinate. So this reaction is can be considered as the redundant. Okay, we can see here, if I am giving numbers, so let this be 1, 2, 3, and this is 4. So if I am calculating the ds value, ds is R minus E, where R is the number of unknown reactions. There are 4 unknown reactions, and for a 2D beam the number of equations of equilibrium available are 3, so it is 1. So I require to consider one reaction as redundant. So I'm considering this particular reaction as the redundant. So if I'm removing this, the system becomes a cantilever beam, which is a determinate structure. So I have identified the redundant. So this equation dou u by dou r in our case is going to be dou u by dou rb, because rb is the one that we have considered as the redundant. Fine. Now let's solve it. So we want expression for m. So we need to identify how many segments are required and all those things need to be done. So we are going with that. So the table we know S, E, L, O, M and m dot. M dot is basically dou u by dou rb. Okay. So we need to identify how many segments are needed. So let's consider that. So if you're considering here location of point load 1, 2 and there is a free end. So here we require 2 segments, segment 1, segment 2. Okay, so let's consider segment 1. When I'm considering segment 1, I will be taking the section in segment 1. Okay, so now I will be thinking which side I should look, left or right. I'm placing it here. The right side is having no forces, left side is having lot of forces. So the best thing is look to the right, right? If we want to look to the right, consider this as the origin. Okay, so I'm considering C as the origin. If C is origin, what will be the limit for the segment? If this is 0, this point is 2. So segment 1 is 0 to 2. What about the EI? EI for segment 1 is EI. So we'll be putting it as EI. Then we need to get the expression for M. So the distance x is from the origin. Okay, this is the origin. So this is distance x. So what will be the moment? At this section, the moment will be, if I'm looking to the right, because origin I have considered on the right. So there is no load, which means the moment is 0. Now, what will be differential of 0? 0. So that's the first segment. Now we need to think about the second segment. Oh, so what are there in the second segment? Second segment, I will be taking the section somewhere here in the segment 2. Okay, segment 2. So now I need to look to the right or left. Which one will be preferable? To the right, because there will be just one. If I'm looking to the left, there are a lot of things. So I'm looking to the right, and my RB is on the right. So I'm looking to the right. So what should be kept as the origin? Either you can keep C as the origin or you can keep B as the origin. Anything is fine. So for a change, I'm keeping B as the origin. Let's see how it will be. So I'm considering B as the origin. If B is the origin, this distance will be X. Okay. The distance to the section from origin is should always be considered as X. So what about the EI value of segment 2? Segment 2 is having a EI value 2EI. Okay, it is 2EI. And what will be the limit of segment 2? If this is the origin, the limit is 0 to 5. Okay, because this distance is 5 meter. If this is 0, this will be 5. So segment 2 is from 0 to 5. Now, what about the expression for bending moment? Let's see that. So if I'm taking a section here, there are 2 forces. One is this point load, other one is UDL. So 2 villains. So let's go for Rajinikanth principle. So first I'm considering the villain RB. What will be the moment due to RB? Force is RB, lever arm is X. So moment is RBX. What about the direction? Whether it is positive or negative. So I considered this is the fixed point and the load is applied in the in-between point, and the shape is sagging, right? It's bending in a format like this. So it is basically sagging, hence it is positive. Now the rest is, the second villain is the UDL. So UDL is acting at a distance of, this distance is 2 meter given in the problem. This is X. So what is the total length of UDL? Total length will be 2 plus X. Okay, so the length is 2 plus x. And what is the value? It is 2. Okay, so w into 2 plus x is the magnitude. And what about the point of action of this UDL? Will be at the center, which means 2 plus x by 2. Okay, because this total length is 2 plus x, so center will be 2 plus x by 2. That is the point where this UDL can be concentrated, so that becomes the lever arm. So the force is 2 into 2 plus x, the lever arm is 2 plus x by 2. Okay, and we need to assign a sign for that. So this is the case, the load is acting like this, it is bending in the hogging shape, which means minus, right? Now we need to get the differential. When I differentiate this, the first part will give me the value x. Okay, dou rbx by rb is x. What about here? This is a constant term. When I differentiate it with rb, the value will be 0. Okay, so I don't have to, so I'll be getting basically this as the condition. So I have all the required terms. Now it's simply the substitution. So as per theory of least work, this can be equated to 0. So I'm equating this to 0. So what will be the expression that I will be getting here? So substitute the different values what we have. So here there are two segments. So dou u by dou rb is equal to, first I need to consider segment 1. What is the limit of segment 1? The limit is 0 to 2. Now what is expression for capital M? 0. Dou m by dou r or m dot, that is also 0. dx by ei value is ei. So that's for the segment 1. Now we consider segment 2. Limit is 0 to 5. Fine. M is this long expression. Let's consider that. rbx minus, this can be represented as 2 will get cancelled. Okay, so it is rbx minus 2 plus x whole square, okay, into m dot. What is m dot here? It is x. dx by ei value is 2ei. Okay, this can be equated to 0 as per theorem of least work. Now when multiplication with 0, this term vanishes. So what left is this. So here we can see that this calculation is going to exceed to the next page. So we are first starting in a fresh page. So we have this. Now we are going to expand this. So this term is 0. Now we are going to work on this. Okay, this is 0 because the multiplication of 0. So this can be written as, the first term goes away. So 0 plus, what about this? So I'm expanding it. So what I'll be getting is integral 0 to 5 rb x square. Okay, x into x rb x square. Then when I expand this, this is a plus b whole square. That is a square plus b square plus 2ab. Okay, so minus a square, that is 4x. Now here b square, that is x square into x minus x cube. 2x, that is 2ab, which means 2 into x, that is 4x into x minus 4x square dx can be equated to 0. Now what will this become? rb integral x square dx, that is x cube by 3 in the limit 0 to 5. This will be 4x. So 4x square by 2 within the limit 0 to 5. X cube becomes x raised to 4 by 4 in the limit 0 to 5. And 4x square becomes 4x cube by 3 in the limit 0 to 5. Okay. This can be equated to 0. Okay, this is equal to 0. Now, so we can now just move to the whole page. So we have the values and we are going to continue calculating the value for RB. Fine. So we have this. Now what? So I'm substituting the value. So this equation becomes RB into 5 cubed by 3 minus 4 times 5 square by 2 minus 5 raised to 4 by 4 minus 4 times 5 cube by 3, okay, equal to 0. Now we can solve this to get the value of RB. When you solve this, you are going to get, you can take all these negative terms to the right hand side. So it's basically 4 into 5 square by 2 plus 5 raised to 4 by 4 plus 4 times 5 cube divided by 3. Okay, I'm taking this to the right side. So multiplied by 3 divided by 5 cube. And I'm going to get the value as 8.95 kilonewton. Okay, so I have the value of RB as 8.95 kilonewton. Now we are going back to the beam with reactions or beam with forces we have earlier written. That is what we were having was something like this: RA, HA, MA, RB, and there was the load 2 kilonewton per meter. Now you can see here we have the value of RB, which is 8.95 kilonewton. Now if you look into it closely, what we have are just 3 unknowns: RA, HA and MA. So 3 unknowns, and the rest everything are forces. It's a 2D beam, so 3 equations, 3 unknowns, 3 equations. Now this is a determinate structure which can be solved using the equations of equilibrium. Okay, so when I try to calculate ds of this now, so ds is number of unknowns 1, 2 and 3. Okay, this is no more an unknown. Number of equations 3, ds is 0, which means it is determinate. Okay, now the beam has been converted into a determinate beam. Now you can use the equations of equilibrium. So I'm writing the first equation of equilibrium, that is sigma fx equal to 0. So you can see here we need to have a positive direction for the system. So I'm considering for the x direction this as positive. So what are the forces? HA is there to the right. There are no other forces, which means HA equal to 0. So I got that. Now I'm trying to calculate sigma MA equal to 0. I'm taking moment with respect to the point A. So when we take sigma, then it's the sign convention is clockwise, anti-clockwise. There is no need for you to go for sagging hogging. Okay, so sigma MA equal to 0. So at point A, there is a moment MA, which is clockwise. Then we have 2 villains. So we are handling 1 villain at a time. So I'm considering RB. So the moment due to RB will be, we know that this is 5 meter, this is 2 meter. Okay, so RB times 5. So the magnitude is RB times 5. What about the direction? Direction is anti-clockwise. Because of the load, it rotates anti-clockwise, which means minus. And the value of RB that we can substitute in the last. Then there is a UDL. So it is 2 kilonewton per meter. Okay, for 1 meter it is 2 kilonewton. For 7 meter it will be 2 times 7. So 2 times 7. And what about the point of application of this UDL? Will be at the center. So whole length is 7. So 7 by 2. And what about the sign? So when I hold it here, the load is acting like this. It will make the beam rotate clockwise. Hence it is positive equal to 0. Now we have the value of RB that we have already calculated. It is 8.95. Fine. Now just calculate the value of MA from this. So we'll be getting it as 14. 2 cancels away. So what left is 7 times 7, that is 49. Okay. When it goes to the right side, it becomes negative. So minus 49, and this becomes plus 5 into 8.95. So what we are going to get is minus 4.25 kilonewton meter. And what is this minus signifies? Minus signifies that the direction what we assumed for MA was clockwise, And when we got negative, it means that in reality, the direction of MA is not clockwise, it is anti-clockwise. That's the meaning of this. That's the meaning of this negative term. Now, the last value what is unknown is Ra. To get that, I'm calculating the equation sigma Fy equal to 0. So I need to have the sign convention. I'm considering all for Fy, I'm considering this as the sign convention. Whichever is upward is positive. So the forces what I have is Ra upward, Rb upward, and downward what I'm having is 2 kilonewton per meter. So this is 7 meter. So 2 times 7 equal to 0, negative because it is acting downward. So the value of Rb is already available with us, which is 8.95. So we can calculate the value of Ra. Ra is going to be, we are going to get it as 5.05 kilonewton. So now we have all the unknown values. In the beam that we started with, we're having unknowns as Ra, Ha, Ma and Rb. Now we have the value of Ra, Ha, Ma and Rb. So it's analyzed completely. All the unknown reactions has been solved. So now the next part is the representation of this as diagrams, that is bending moment diagram and shear force diagram, that you can try on your own. Thank you.